this light over there.
Okay. Can you hear me? So I'll speak about regional strategies and roadmaps, a community vision from the Americas. I'll talk first about the United States, and then Canada, Brazil, Mexico, Argentina, and briefly mention other countries. In the United States, the strategic plan is called Building for Discovery. The charge was to develop a plan executable over 10 years in the context of a 20-year global vision. The US community came together to make this plan in a two-step process. First, SNOMAS, where all of the community was involved, and then P5, which was a committee. The SNOMAS process started in October 2012. It was a year-long community-wide study organized by the American Physical Society, and it was absolutely invaluable for the strategic plan. When we got together to discuss as a community, we recognized that it was a very special time for particle physics. That year, the Higgs had been discovered. 1 year later, it won the Nobel Prize. Preceding that, in 2011, the accelerated expansion of the universe had won a Nobel Prize as well, and there had been the discovery of large neutrino mixing with theta 1-3. At the same time, there was unprecedented interest in particle physics. A prime example of that was the Large Hadron Collider. The experiments and the observation of a Higgs boson became a global phenomenon. It changed our relationship with the public, an opportunity to expand engagement with the public and our colleagues in the universities and our governments in all of our nations exists. And we wish to communicate what we have learned and the opportunities for discovery in particle physics. In other words, the community called upon P5 to develop a narrative for our field. The narrative must explain to the governments of the world and to the public why the world needs a healthy particle physics program. There's at least 3 reasons. One is our science is important for nations to pursue. For millennia, all great societies have asked these questions. Of course, today we ask them in a slightly more modern language like this. But the most important thing about this is that there are so many questions. What Newton once said, what we know is a droplet, what we don't know is an ocean, is even more true today than it was when he said this 300 years ago. And it's that fact that is reason 2 for why we need a healthy particle physics program. It is because the big questions we ask attract young talent to all of the sciences, not just to particle physics, but to all of them. And number 3, particle physics is an essential part of the fabric of the physical sciences of developed nations. It contributes broadly to other physical sciences through accelerator science, detector development, large-scale computing driven by large collaborations, but it's also a two-way street. Other physical sciences contribute to particle physics. And so we asked, what should a healthy particle physics program in the United States look like? Some of the essential ingredients would be a program focused on the most compelling science, infrastructure to support the development of our tools, and a long-term vision and strategy to guide the program for future decades. And so more than 1,000 physicists came together in the United States and around the world. A vast number of scientific opportunities were investigated and discussed and summarized in SNOMAS reports, and it was an essential input and starting point for P5. Our resource book, similar to the physics briefing book of the European Strategy Group, conveys the health and the diversity of the field in the US in a global context for our colleagues and for our fellow citizens. It was the first version of the compelling narrative. What SNOMAS did, to recap, was to evaluate by benchmarking, speculate by calculating. We dreamed about following the physics. We proposed the methods and the experiments to make the discoveries. What we did not do was set the priorities. That was a job of P5, the committee that came afterwards. Now, during the P5 process that began in the autumn of 2013, the community input continued to flow to P5. There was a continuous effort to maximize community interactions. There were big, open, topical meetings, community town halls, discussions, and an input portal. The P5 report was presented to the High Energy Physics Advisory Panel of the DOE and the NSF, the 2 funding agencies in the United States, on the 22nd of May 2014, and was unanimously accepted. It contains 29 recommendations. Only the main points can be summarized here. The first of them is that particle physics is global. The United States and major players in other regions can together address the full breadth of the field's most urgent scientific questions if each hosts a unique world-class facility at home and partners in high-priority facilities hosted in other regions. Hosting world-class facilities and joining partnerships and facilities hosted elsewhere are both essential components of a global vision. The strong foundations of international cooperation exist, never more so than in the case of the Large Hadron Collider at CERN, which serves as a superb and prime example of a successful large international science project. Reliable partnerships are essential for the success of international projects in general and in particle physics in particular, and this global perspective is finding resonance in a historically competitive field. Look at the European Strategy Group for Particle Physics report in 2013. Read the report of the Subcommittee on Future Projects on High Energy Physics in 2012 from Japan, and you will find the same thing. So our recommendation number one was to pursue the most important opportunities wherever they are and host unique world-class facilities that engage the global science community. The second thing was that P5 distilled the many questions identified by SNOMAS into 5 compelling lines of inquiry that show great promise for discovery in the next 10 to 20 years. They called them the science drivers, and they are using the Higgs boson as a new tool for discovery, pursuing the physics associated with neutrino mass, identifying the new physics of dark matter, understanding cosmic acceleration, both the late-scale dark energy and the early-time inflation, and to explore the unknown, new particles, interactions, and physical principles that govern them. The science drivers are deliberately not prioritized because they are intertwined, probably much more so than we currently understand. However, the projects were prioritized. The vision for addressing each of the drivers using a selected set of experiments is given in the report, along with their approximate timescales and how they fit together into a coherent program. So recommendation 2 was to pursue a program to address these 5 science drivers. And so the vision that starts from the science drivers, driven by the community discussions and to and fro between the community and P5, and the criteria to guide project selection led to the development of the program that you'll now see. First, the enormous physics potential of the LHC, which is truly exciting to all particle physicists. Now that we're entering a new era with its planned high luminosity upgrade should be fully exploited. Recommendation 10, complete the LHC phase 1 upgrades and continue the strong collaboration in the LHC with the phase 2 upgrades of the accelerator and both general purpose experiments. The LHC upgrades constitute our highest priority near-term large project. Number 2, the Mu-T-E and Mu-G-2 projects at Fermilab are immediate targets of opportunity in the drive to search for new physics, and they will help inform future choices in this direction. Recommendation 22, complete the Mu-T-E and Mu-G-2 projects. Neutrino oscillations. Short and long baseline oscillation experiments drive currently probe 3 of the science drivers in the neutrino area. And there is a vibrant international neutrino community invested in pursuing the physics of neutrino oscillations. The US has unique accelerator capabilities at Fermilab to provide neutrino beams for both short and long baseline experiments, with some experiments underway, and a long baseline site is available also in South Dakota. And so many of these current and future experiments and projects share the same technical challenges. Interests and expertise in neutrino physics and detector development of groups from around the world, combined with the opportunities for experiments at Fermilab, provide the essentials for an international neutrino program. Recommendation 12, in collaboration with international partners, develop a coherent short and long baseline neutrino program hosted at Fermilab. Now, the long baseline neutrino program in the US has undergone multiple significant transformations since the 2008 P5 report. It was originally formulated as a primarily domestic experiment. The minimal configuration with a small far detector on the surface has limited capability. A more ambitious long baseline neutrino facility has been urged by the SNOMAS community study and expressions of interest from physicists around the globe. And to address even the minimum requirements specified in the P5 report, the expertise and resources of the international neutrino community are needed. And so a change in approach was therefore recommended. Form a new international collaboration to design and execute a highly capable long baseline neutrino facility hosted by the US to proceed. A project plan and identified resources must exist to meet the minimum requirements in the report. The OBNF is the highest priority large project in its time frame. the Proton Improvement Plan at Fermilab. A necessary investment in physics capability, it will enable the world's most intense neutrino beam, providing the wideband capability for LBNF, as well as high proton intensities for other future opportunities. It's an investment also in national accelerator infrastructure. Recommendation 14, upgrade the Fermilab Proton Accelerator Complex to produce high-intensity beams. Hints from short baseline experiments suggest possible new non-interacting sterile neutrinos or non-standard interactions for ordinary neutrinos, and these anomalies can be addressed in a variety of techniques. Recommendation 15, select and perform in the short term a set of small-scale, short baseline experiments that can conclusively address experimental hints of physics beyond the 3 neutrino paradigm. Some of these experiments should use liquid argon to advance the technology and build the international community for LBNF at Fermilab. The ILC. Participation by the US in the ILC project construction depends on a number of key factors, some of which are beyond the scope of P5 and some of which depend on budget scenarios. As the physics case, though, is extremely strong, we plan in all budget scenarios for ILC support at some level through a decision point within the next 5 years. If the ILC proceeds, there is a high priority option in the highest funding scenario to enable the US to play a world-leading role. If the ILC does not proceed, then ILC work would terminate, and those resources could be applied to accelerator R&D and advanced detector technology. Recommendation 11, therefore, is motivated by the strong scientific importance of the ILC and the recent initiative in Japan to host it. The US should engage in modest and appropriate levels of ILC accelerator and detector design in areas where the US can contribute critical expertise. Consider higher levels of collaboration if ILC proceeds. Now, medium and small projects in areas especially promising for near-term discoveries and in which the US is in a leadership position should move forward under all budget scenarios. Second and third generation dark matter direct detection experiments, the particle physics components of the Large Synoptic Survey Telescope, and cosmic microwave background experiments, both stage 3 and stage 4, and a portfolio of small neutrino experiments. Another important project of this type is a dark energy spectroscopic instrument that would also move forward, except in the lowest budget scenario. And there's an importance of a diversity of scales. With a mix of large, medium, and small projects, important physics results will be produced continuously throughout the 20-year P5 timeframe. Now, specific investments should be made also in essential accelerator R&D and instrumentation R&D. The field relies on our accelerators and our instrumentation, and on R&D and test facilities for these technologies. There's a number of recommendations bearing on accelerator R&D. I can only mention 2. First, the Very High Energy Proton Colliders. A Very High Energy Proton Collider is the most powerful future tool for direct discovery of new particles and interactions under any scenario of physics results that can be acquired in the P5 time window. Accordingly, recommendation 24, participate in global design studies and critical path R&D for future Very High Energy Proton Colliders. Continue to play a leadership role in superconducting magnet technology focused on the dual goals of increasing performance and decreasing costs. And in scenario C, which is the most optimistic of the funding scenarios, there are 3 options to proceed, one of which focuses on accelerator R&D. The US could move boldly towards development of a transformational accelerator R&D program. There are profound questions to answer, but going much further with accelerators requires changing the capability cost curve of accelerators, which can only happen with aggressive, sustained, and imaginative R&D. For example, the primary enabling technology for PP colliders is high-field accelerator magnets, possibly with more advanced superconductors. And for E+, the primary goals are improving the accelerator gradient and lowering the power consumption. Within the US, there's a detailed vision and roadmap that should be articulated by the upcoming HEPUP subcommittee on accelerator R&D. As work proceeds worldwide on long-term future generation accelerator concepts, the US should be counted among the potential host nations. And experience suggests that this effort will also have large positive impacts beyond our field. Now, the reaction of the report was that it was unanimously accepted on the 22nd of May by the High Energy Physics Advisory Panel. In Washington, the report has been well received. The community in the United States has received it well as well, both at the HEPUP meeting, at virtual town halls, at conferences and workshops. The P5 report today is backed by the US particle physics community, and we can say that there is a consensus. In just 7 days, over 2,000 members of the community, that's about 70% of those in the United States, signed the letter shown here to support the P5 report that was addressed to Secretary Monitz of the DOE and Director Cordova of the NSF, and that letter was submitted to that on June the 29th. And to be clear about the United States system, P5 provides the science drivers and recommended strategic options, particularly project priorities. HEPAP, the advisory panel to the agencies, is the keeper of the plan and reviews the implementation and progress. The agencies, the DOE and the NSF, are the stewards of the program. They receive the advice and try to implement the plan as best they can with the actual budgets given to them by Congress. To quote Andy Langford, the chair of HEPAP, "I believe that the agencies understand our report and recommendations and are taking it on board. The US particle physics community shares this view. The DOE is already taking steps to implement recommendations which will affect the fiscal 2015 budget, and Nigel Looking can tell you more about those implementations." Moving to Canada, Canada's last long-range plan was in the period 2011 until 2016. The major initiatives in particle physics are ATLAS, T2K, SNOLAB, support for other smaller projects as well, and theory, and for the SRF aspects of the Aerial Accelerator. Looking beyond 2016, the report cites Aerial, the ATLAS upgrade, EXO, ILC, both SRF, TPC, and calorimetry, SNOLAB for neutrinos and dark matter, BEL 2, T2K, and ultra-cold neutrons. One quote from the report is shown here: "The ILC calls for SRF cavities, and Canadians are developing the expertise to be able to construct such cavities here in Canada, working with industry. Through this project, Canadian universities are working to develop graduate programs in accelerator physics to train the next generation of Canadian accelerator experts and are actively recruiting graduate students." Hand in hand with the Canadian subatomic physics plan as a long-range plan for TRIUMPH. And one quote from there: "The Linear Collider project, TRIUMPH is invited to play a role in the initial project, largely following from the highly successful accelerator contributions to the LHC and recent accomplishments for Aerial Electron Accelerator. The Linear Collider will open up new and exciting opportunities for Canadian researchers and students, as well as Canadian high-tech industry. Construction of the Linear Collider will start once international agreements have been reached, and the facility would take 10 years to build, but Canada, via TRIUMPH, will be there when it is. Canadian subatomic physics is launching another long-range plan. The process starts in 2015 and will conclude with a report in 2016. Moving to Brazil, there are more than 300 theorists and 180 experimentalists in Brazil today. Current activities include more than 130 experimentalists working at CERN on all of the LHC experiments and at Fermilab on neutrino experiments, as well as in Pierre Auger Observatory and in Double Show. In the future, the level of activities at CERN will be maintained. Brazil is participating in the upgrades to all 4 experiments. In neutrinos, all groups are joining the LBNF. That's 25 physicists from 6 institutes. And in astroparticle physics, a proposal to join CTA is being discussed. In Mexico, there is growth across the sciences in Mexico. This plot shows the number of PhD researchers in 2002 in red, 2009 in light blue, and 2013 today in the darker black color. And particle physics is shown with the arrow. This wonderful growth includes now 138 PhD-level researchers, of which 30 are experimentalists. This doesn't include the postdocs, the students, the engineers, and the technicians. Activities include Auger, CMS, HOOK, an experiment at JLab, Minerva, and Theory. In Argentina, there are 60, of which 50 are experimentalists. The current activities include ATLAS, HEP phenomenology, Pierre Auger, and accelerator physics. In the future, the community is growing. They'll broaden their contributions in ATLAS as a national grid initiative ongoing. In astroparticle, Auger will be upgraded, and there's a proposal to build CTA in Argentina. It's one of many possibilities, and that's being discussed. And there's also vibrant HEP programs that are growing in other Latin American countries, including Chile, including Colombia, including Cuba, Ecuador, Peru, but there's insufficient time to cover them in this talk. So particle physics is global. That's both a challenge and an opportunity. ICFA has recognized this. In a statement they produced yesterday, they said, ICFA endorses the particle physics strategic plans produced in Europe, Asia, and the United States, and the globally aligned priorities contained therein. They went on to say, here, ICFA reaffirms its support for the ILC, which is in a mature state of technical development and offers unprecedented opportunities for precision studies of the newly discovered Higgs boson. In addition, ICFA continues to encourage international studies of circular colliders with an ultimate goal of proton-proton collisions at energies much higher than those of the LHC. So to conclude, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. This is our challenge. We are a global field. If we rise to that challenge, we can one day learn how the universe came to be, how it will evolve, and how it will end. And the particle physics in the Americas is truly engaged in this global effort. Thank you very much.
Thank you very much, Ian. Any questions or comments at this stage for Ian's talk? Okay, if not, there was, yes, please, excuse me.
Thank you very much for your talk. When I was working in the US, I got an impression that US Congress was trying tough to reduce the budget deficit. And you mentioned here a very ambitious particle physics program. Do you think that there is a good chance that US Congress would approve this program? I'm sorry for my naive question.
He said that when he was at US, there was a budget deficit, and then under the circumstances of budget deficit, can they really approve the budget which corresponds to fulfill such a program?
So, I mean, the way in which I believe there's a great opportunity today to change the conversation in Washington. Particle physics historically, many, many years ago, in the United States, grew out of the bomb project. It had a special relationship with government, and it didn't have to fight very hard for its resources. With time, other sciences grew up, had very compelling and exciting cases of their own, and many supporters. And so the share of particle physics funding in the United States relative to other sciences has declined. However, what we found after the discovery of the Higgs, we organized a visit to Washington, where we brought together the US particle physics community, and we held a reception to celebrate the discovery of the Higgs and particle physics. Politicians lined up to volunteer to speak at that meeting, politicians from the Republican Party and politicians from the Democratic Party, and they talked with passion about the need to invest in fundamental science, including particle physics. And so I do believe that there's great breadth of support in Washington today. And that's why we went to such trouble in the United States to develop a compelling narrative. And that P5 report is the compelling narrative. And I believe that we can optimistically expect that we will see more funding in the future for particle physics. That letter, signed by 2,000 scientists, speaks to that in the sense that the community is fully behind the report. In August this year, we will visit every single district in Congress when senators and congressmen return home. We'll take that letter with us. Young people will talk with passion about physics and about science in general. If we can get science funding up in the United States overall, particle physics will come up too. And so that's our goal. And we share that with our brothers in biology, our brothers in chemistry, and in other fields as well. Does that answer your question? Thank you.
So we take one more question here, and then we have to proceed, I think, next, please.
So we have ECFA in Europe and ACFA in Asia, and it doesn't seem that we have a similar thing for Americas. So shouldn't we have some sort of at least the bottom-up organization that has a communication channel open in North and South America?
There is an ECFA in Asia and an ECFA in Europe, which discuss the matters in regional issues. Regional issues, while in the US or in the Americas, it doesn't exist. So we shouldn't want time to think about such a pan-American organization.
Yeah, this is a very good suggestion. We were talking about this at lunch today. We do need, I think now, to create an organization corresponding to ECFA for the Americas. It would be very appropriate. So many regions within America, in Latin America, smaller countries are becoming much larger very rapidly. They want to engage. One of the ways they can engage is regionally and globally. And so I believe that we should welcome all of the newer countries and help them organize to participate fully in particle physics wherever it is. whether it's in the Americas or elsewhere. And so it'd be entirely appropriate to create an organization that corresponds to ECFA for the Americas. In fact, there are organizations like that for certain special projects. For example, the Linear Collider has a committee for the Americas, and they're talking about making sure that that really is the Americas and not just North America in the future. But we can go much further and include all of particle physics in that way. So thank you for that very good suggestion.
Okay, thank you very much.